So the presentation I'm giving today is trying to give our perspective, IWS's perspective on laser processing with a special emphasis on solutions for industry. And when I say our, I mean our, because this is certainly a team effort. You see a long list of contributors here, and I'm very grateful to them for providing me with the information that I'll be presenting now. Now, as I said, this is kind of an overview, a comprehensive overview of our perspective of laser materials processing at Fraunhofer IWS. And the aim of the talk is really to go through a number of topics that we have been following for the last years, and where we have latest developments that I'd like to share with you. And the first topic I'd like to start with is dynamic beam shaping for high performance laser welding. And I'll kick off this part of the presentation with showing you an example from industry where aluminum die cast parts are welded using static laser beam welding to aluminum sheet material in this case. And all of you who are familiar with that know that the weld seam looks like Swiss cheese, if I may say that. So there's a lot of porosity involved. So if you need dense and pressure tight weld seams, this is certainly a big challenge to be overcome. And one solution to do that is to use electron beam welding, which is of course a little bit more costly than laser beam welding because it's been done in a vacuum chamber. And as you can see from this picture here, you do not really get rid of porosity. There are still some pores in. It's much less than in the case of laser beam welding, but anyway, there's still, it's not not yet fully dense. So our approach to tackle this problem is to use dynamic beam shaping, and I will show you the next slides how this works, in order to minimize the porosity of the weld seam. And the result has been shown here, and it's, I think, a very impressive result, showing only minor porosity here, which is really not critical for the application. So looking at a dynamic beam oscillation or dynamic beam shaping in more detail, this video here says more than 1,000 words, I believe. So what you can see here is in cross-section an observation of the melt pool and the formation of bubbles. So this is on the left-hand side, the conventional process where you have a lot of bubbles, gas bubbles developing during the processing, and well, they will be entrapped in the weld seam and they will leave us with porosity. Now, when we switch on the dynamic beam shaping at this line here, you see all of a sudden the melt pool is calming down, the number of bubbles being developed is much reduced, and therefore we have a very stable process, an active stabilization of the laser beam welding process by this dynamic beam shaping using a 4 kilohertz frequency. So we have a very tight control over the melt pool by using this beam shaping and beam oscillation, tightly controlling the process, and very much improving the welding result. Now, knowing about the physics and the principle, we have developed an industrial solution in terms of the welding head, which is called RemoWeld Flex. And in the standard version, we're using a 2D beam oscillation by using a galvo scanner. The principle is shown in this video here on the right-hand side, 4 kilohertz, I already mentioned that. And in the optional package, you can also use seam tracking or cameras to get a better hand on the processing while you weld. So the next step, the future, will be to develop and this is just under development as we speak, to develop a 3D head using also that direction, so the z-axis, for controlling the energy input into the melt pool. And this will be complemented by extensive sensoring using high-speed cameras, a thermal camera, as well as a microphone using acoustic emission to sense the welding process. And this data will then be fed into an AI-based data processing system that is feeding back information to the laser control system. So we have a feedback control using AI software and methodologies in order to further improve the welding process. Now, the next example I like to briefly touch upon is from the high-speed laser cutting activities in our lab. And the motivation here is clearly to get a very high flexibility using laser cutting over the conventional mechanical cutting technologies such as shear cutting. Certainly the beauty of using a laser is there's no tooling time anymore, and various materials can be cut, ranging from high strength steels to softer materials like aluminum or copper and other alloys. Now, when speaking about high speed, I really mean high speed. And as you can see from this slide here, we are shooting for 500 meters per minute and even higher. And this is part of a study here that shows how a combination of a certain optical setup, we used three different optical setups, 1, 2, and 3, and laser power and speed gives you different cutting results. And as you can see here, for the highest speed, you have to increase the laser power. This is 430 meters per minute, and the cutting results are still strikingly good. Now, this has been implemented again since we are providing information help to industry into a pilot machine concept. What you can see here is a pilot slitting machine for electrical steel of 270 micron thickness. We're using a single mode fiber laser with 2 kilowatt in laser power, nitrogen or compressed air at a pressure of 15 bar, and the fade rate of the sheet is 200 meters per minute, and we have successfully proven the principle of high-speed laser cutting with this type of machine. Now, quickly moving on to the next topic, which is laser structuring for the improvement of grain-oriented silicon steel. Now, the background for this type of development is that electrical transformers are using grain-oriented silicon containing steel, and these transformers, they suffer from losses, electrical losses, due to the magnetization of the transformer, and they also produce noise. And those of you who have ever been next to a transformer know that they can be very noisy. So reducing the electrical or magnetic losses as well as reducing the noise is the aim of this type of development here. And in our lab, we have developed the so-called laser structuring methodology, where we structure the surface of electrical steels, which I will show you in more detail in the next slide. Now, what you can definitely see is the improvement, the degree of improvement that we can achieve on the left-hand side here on the bottom of the slide, 14 to 15% improvement over core losses by using improvement by domain refinement of the grain-oriented silicon steel. So in order to be able to do that, we are using our expertise in laser domain refinement systems, optics and control design, as well as technology development, and we have recently developed a highly dynamic beam deflection system accompanied with a scanner and a laser control system. And we are basically following two different approaches with the structuring technology here. The first variant is shown on the left-hand side, which is a purely thermally induced domain refinement, where we use the laser as a heat treatment tool, and we refine the magnetic domains by using heat through thermal stresses. This effect, of course, is not annealing resistant. So when you heat up the electrical steel sheet, you will lose this effect. Anyway, this is used for stacked transformer cores in industrial application. Now, on the right-hand side, the second variant of this technology is depicted, showing that we form grooves into the sheet material. So we are retracting material from the surface. So there's a geometrical change in the surface. And this leads again to domain refinement by structures. And these structures, of course, they're annealing resistant, and therefore heat treatment does not harm this effect. This technology is then used for wound cores of transformers in industrial application. Now, again, in order to demonstrate this technology on an industrial level, we have set up a verification platform for developing various control solutions, which is shown here. We have already heard about it earlier in the conference, so I will be very, very brief here. So this machine can mimic these processes at an axis speed of 90 meters per minute and a spot velocity of 300 meters per second. So it's quite a speedy process, but you always have to deal with large surface areas, so it needs to be a speedy process, which is highly controlled using again smart control systems that are in-house developments. Now, I'm moving forward, showing you quite an unusual use, you might think, when you see the pictures on the next slide for lasers. And this is lasers for ammunition disposal and dismantling. So just a few background information here. In Germany, even 76 years after World War II, there are still tens of thousands of unexploded ordnance in the ground. So there are bombs and other things still buried in the ground from World War II. And they, of course, impose a big danger on the public. And here's some accidents that happened, or some issues that occurred with construction and where they discovered these ammunitions. So disposal and identifying and then disposal and maybe recycling of these ammunitions is key. And if you look at this map here, this shows you the estimated amounts of ammunition buried in the ocean. This is the North Sea, this is the East Sea, the Baltic Sea, and in Europe. So 1.3 million tons, and this is 300,000 tons of war debris, if you will. So this poses really a danger. So the state-of-the-art process is to, of course, first of all, find the ammunition, then remove the detonator or the igniter, if you will, and this leaves you with an explosive chemical in a metal shell, in a metal container. And in order to recycle or dispose this part of the ammunition, you have to separate the shell from the chemical. And this is typically done, conventionally done by just sawing the metal here, remove then the chemical and dispose or recycle the metal. Since the sawing process is so time consuming, the depots for ammunition are overflowing. So it's a lot of ammunition that needs to be stored. And of course, one wants to get rid of that. So our solution to this challenge and to this problem is to use the laser as a cutting tool rather than a mechanical saw. And this on a first glimpse seems to be quite crazy to do that. But as a matter of fact, the laser cutting provides you with a minimum heat input into the process. And either you can do that in the open atmosphere in air or underwater, as you can see here on the right-hand side. So the laser is used as a cutting tool in this case to softly separate the material and then finally get access to the chemical that can be taken out then, and the two parts can be recycled or disposed. All right, so coming to the next topic here, which is additive manufacturing of pure copper. And we've already seen a number of talks on additive manufacturing during this conference here. And I would like to pick out one topic that we've been following quite recently, but very successfully, and that is additive manufacturing of copper. Now, everybody who's involved or who's been in touch with laser interaction with copper knows that copper has a fairly low absorption with regards to solid state laser radiation. So the wavelength of 1 micron is really unsuited to manufacture copper parts. I mean, as you can see, absorptivity is very low here. Now, a key for solution for solving this problem with absorption is to use laser wavelengths, which are much shorter. So, for example, the green wavelength at 550 nanometers, which is here, has a much higher absorptivity for copper, or copper has a much higher absorptivity for this wavelength. And this is now key for solutions that we've followed, both in terms of laser powder bed fusion as well as for laser metal deposition. And this picture on the right-hand side shows a very sophisticated nozzle design that we've recently developed for open air titanium additive manufacturing using laser metal deposition. So it's an in-house development, if you will. So we need this this copper part for a certain nozzle. Now, the project that I would briefly introduce to you here is even more fascinating, I believe, because this project here is dealing with a linear accelerator made out of copper, as you can see here. Fairly complex shape, fairly complex geometry. It's a radio frequency quadrupole made out of copper. And well, the conventional way of doing it is to machine parts from a block of copper and then assemble it. And the problem with additive manufacturing, of course, has been so far that the infrared laser sources need a lot of energy and a high energy input during the processing, which leads to a small overall efficiency, and also the danger of damaging the optics due to the backscatter of laser light. So the solution is definitely a green laser source that we've used in our lab here for not only fabricating benchmark geometries where we check the process and develop the process itself, but also to fabricate the parts. And you can see some of the examples of these parts here: highly porous parts made out of copper. Now, the beauty of using green laser sources is we can achieve a much higher absorption, 280%. And as you can see from the micrographs here, we achieve a fully dense part with almost 100% density, only 0.05% porosity, which is an extremely good result. And looking at the properties, electrical properties, for example, or thermal conductivity, we are even beyond the standard, at least for electrical conductivity, we are beyond the international copper standard data. Now, a second approach, which is also involving copper, is using copper for hybrid manufacturing using LMD, laser metal deposition technologies. And this is just to give you an example. This is a mold insert using copper additions here on the side. So it's steel, you see the steel here. This has copper additions in order to better control the heat of this part. So this shows another aspect of additive manufacturing we're following, which is multi-material AM. Okay, with that, moving further to high power laser cladding. And we had a very nice presentation given by Maria Barbosa yesterday on this topic, so I will be brief here as well. Harder, better, faster, stronger, that's our vision, our approach for further development of this process. And we are here combining high power diode lasers with high feeding rates and high coating speeds. And you see some technical realizations of what I was just talking about, different nozzles, different technical approaches to achieve highest process efficiency for the respective applications. And speaking about applications, I would like to show you this example here, which is a brake disc that has been coated with using very high speed laser cladding in our lab. The processing time here is fairly short. So as you will see in just a second, we can achieve fairly high surface areas per time. So this is about a little bit less than 1 square meter per minute. As you can see here, 650 centimeters square per minute is what we have achieved in the laboratory so far. Now, again, here, the latest development in order to further push the envelope of high speed and high power cladding, I should better say, is the coax quattro development, where we introduce wire and powder in the cladding process. This gives us a high degree of freedom and the possibility of using high power lasers. So the current development is 4 wire nozzles and a 4-jet powder nozzle. And as you can see here, this is suitable for 20 kilowatt of laser power. And with that, we can, for example, use Inconel wire and tungsten carbide powder in order to produce cemented carbide coatings or stellite coatings in situ alloyed rather than using a blended powder, for example. And of course, this LMD process also gives the possibility to do it not only in 2D, but also in 3D. So our developments also move on to additive manufacturing, where I'd like to start the video here, so I need to get rid of the laser pointer, where we use the same technology, wire plus powder, in order to build up 3-dimensional structures. And Maria Barbosa has shown this picture here yesterday already. So with that, I would like to move on to the last part of the laser hardening with temperature field control. And we will have, right after my presentation here, we will have another contribution from IWS on this particular topic given by Marco Seifert. So I can be brief here again, but I would like to share with you this fascinating picture, which shows that with our new technology of laser hardening using a temperature field control system that we have recently developed, we are able to heat treat homogeneously even very complex shaped components. And when I say complex shaped, I mean complex shaped. Look at the shape of this component here. So we have flat surfaces, which is kind of easy. We have a radius here. We have different steps. We have edges, corners, we have V-grooves, and we have even boreholes. And if you look at the coloring of the surface, which comes from the hardening process, of course, it's quite homogeneous, which is a sign for very homogeneous heat distribution. And this can be achieved only by a very tight process control, where we tightly control the heat flow conditions. And these can be adjusted and adapted by locally adjusting the laser intensity and the intensity profiles. So what we do in this in our system is we are using one main controller, but up to 11 local temperature field controllers which work simultaneously. And if we go to the borehole energy distribution, that's probably the most clear picture here. What you can see here is that the energy is shut down where the boreholes are, and particularly the edges are in danger to be overheated. So we need to tightly control the energy input, particularly around the edges here, and where energy is needed in between and at the edges of the circumference of the boreholes, of course, there's energy provided. And by using this technology, we can tightly control the energy input, even on complex shaped geometries. Now, there's a lot of hardware and also software development behind it, and Marco Seifert will certainly provide you with many more details about this. All what we can show here is in-house development and builds upon our long-lasting expertise in laser hardening. And rather than showing you these pictures, I would like to leave you with these fascinating, intriguing pictures as I see and I think, showing the beauty of this technology. Now, this is a curved 3D part which can be homogeneously heat treated. Look at the track of this this heat treatment. Here, very homogeneous heat distribution, obviously, from wide areas to smaller areas, variations in energy distribution, and even the grooved and complex Z-shaped surfaces can be heat treated without great difficulty. Not doable with the conventional process, only with the latest developments. So with that, I would like to come to my conclusion. And how could you conclude such a talk where you have a bunch of different topics for different applications, for different industries? And I try to draw some very general conclusions here. So lasers, as we all know, have matured to indispensable tools for many industries and also many applications, because lasers are, as we all know, productive, they are precise, they are touchless tools, if you will, and they are kind of ever sharp and have other properties, as we all know. They are perfect tools for many applications and many industries. There is certainly a huge knowledge base on laser processing in both science and industry, and we should keep on using it in order to tackle the challenges, because yes, there are, and yet there are still challenges to be addressed. But there are also opportunities to be seized in terms of markets. Open up new markets that have not been covered by laser technology so far, still reducing the costs, improve the performance, and find other applications, more applications for laser technologies. So for us as a laser community, it's a great field of development, and a great field for developing further technologies. So that should leave us with just pressing the start button and go for it. Okay, so with that, I would like to stop here, and thank you very much for your kind attention and your interest. And that's all I have. Thank you.